My name is Pragya Gambhir and I am an MTech student at IIT Delhi. Today I'll be presenting my research titled Investigating the Molecular Properties and Crystal Interactions using ORCA and CrystalExplorer. Under the guidance of Dr. Sajesh P Thomas, this study explores molecular stability and interactions in small organic molecules, combining advanced computational tools like ORCA and CrystalExplorer to derive meaningful insights into structural and energetic properties. Let me start by introducing the main objectives of my research. Using density functional theory and CrystalExplorer, I aim to study the molecular properties like geometry optimization, dipole moments, HOMO-LUMO energy levels, IR spectra, and lattice energies. My work focuses on understanding the structural stability, hydrogen bonding, and pi-pi interactions in crystals. To achieve this, I used the B3LYP functional and the 631G DP basis set in ORCA, while CrystalExplorer helped with the crystalline interaction analysis. By the end of this presentation, you will have gained sound knowledge about key aspects of molecular and crystal property analysis. First, I'll walk you through geometry optimization, which is fundamental for understanding molecular stability. We'll then explore the HOMO-LUMO evaluation, focusing on how these orbitals predict reactivity. Next, we'll look at the dipole moment determination and the IR spectra analysis, which helps us understand polarity and vibrational properties. Moving forward, I'll explain the analysis of lattice energies, which reveal insights into crystal stability. Finally, I'll discuss differences in hydrogen bonding and pi-pi interactions, which are critical for understanding molecular interactions in crystalline systems. For my research, I used two computational tools, ORCA and CrystalExplorer. With ORCA, I employed the B3LYP functional and the 631G DP basis set. Geometry optimizations were performed using the optimization plus frequency keyword to ensure the structures were at energy minima conformed to the vibrational analysis. I also conducted the HOMO-LUMO analysis using single point energy calculations and visualized the molecular orbitals with IBO view. For CrystalExplorer, I used the CE B3LYP method to calculate the lattice energies from the crystallographic information files. Additionally, I analyzed the interaction energy framework, focusing on contributions from the hydrogen bonding and pi-pi stacking. This was done using CrystalExplorer 21 for advanced crystal property evaluation. Let's start with the geometry optimization and the frequency measurement. For this, we drew the molecule in Avogadro and generated an ORCA input file through extension. Then we go to the command prompt and convert the input file to the output file. From the output file, we can obtain most of the results for the chosen molecule. For ethylene glycol, after 7 optimization cycles, the molecule showed no imaginary frequencies, confirming its convergence. The optimized geometry reached a minimum energy of minus 6265.51103 electron volts. I also analyzed the bond distances, angles, and dihedrals for the structural precision. Bond angle, dihedral angle, and the bond distances can be obtained by opening the output file in Avogadro. Its dipole moment was also calculated as 2.52475 dBi, indicating moderate polarity. These results established ethylene glycol's structure foundation for further applications. Again, the geometry optimization was conducted for acetone, and its geometry was optimized over 11 cycles, also showing no imaginary frequencies, which confirm the convergence. The minimum energy for the molecule was found to be 5256.16442 electron volts. I analyzed its bond angles, bond distances, and dihedral angles using Avogadro, and the dipole moment was slightly higher at 2.82090 dBi, reflecting stronger polarity. This stable configuration makes acetone a valuable case study for solvent and reaction modeling. Now on to glycine, an amino acid essential in biomolecular systems. I simulated its IR spectra and observed the major peaks at 3300 and 3400 cm inverse for the NH stretch. Also 2900 cm inverse for CH stretch and 1700 cm inverse for the CO stretches. These peaks align with the experimental data, validating the computational approach. This analysis confirms glycine structure and helps explore its role in proteins. Moving on to 1,2-dichloroethylene, I compared the cis and trans isomers. The trans isomer was more stable by 63.47527 electron volt due to reduced steric hindrance. Its energy was minus 27,150.50486 electron volt compared to minus 27,087.02959 electron volt for the cis form. The dipole moments were minus 2.03361 dBi for cis and 0 dBi for trans, highlighted the symmetry in the trans isomer. These findings demonstrate the significant impact of the molecular geometry on stability. For butadiene, I examined its HOMO-LUMO energy gap. The HOMO energy was minus 0.3228 electron volt and LUMO was 0.1156 electron volt, giving a gap of 0.4348 electron volt. A smaller gap indicates potential chemical reactivity. Visualizing the orbitals revealed pi bonding in HOMO and antibonding in LUMO, pointing to the regions of reactivity. This makes butadiene an interesting molecule for polymerization studies. Now let's look at the electrostatic potential maps. For ethanol, the strong negative potential around the hydroxyl oxygen indicates the hydrogen bonding capability. Partial charges were observed to be minus 0.680 on oxygen, 0.280 on carbon, and 0.400 on hydrogen. Also, for DMSO, the negative potential was localized on sulfur and oxygen atoms, with partial charges as 0.113 on sulfur and minus 0.500 on oxygen. These maps highlight both molecules have a polar nature and are crucial for solvation and interaction studies. Now, using CrystalExplorer, I studied the polymorphism in 5-fluorouracil, an anti-cancer drug. Different polymorphic forms showed variation in stability and molecular packing. Understanding these differences is vital for the pharmaceutical development as polymorphs affect the drug solubility, stability, and bioavailability. This research provides a foundation for optimizing 5-fluorouracil formulation. I compared the two forms, Form A with the lattice energy of minus 26.6 kilojoules per mole and Form B with minus 70.5 kilojoules per mole lattice energy. Clearly, Form B is more stable as its negative lattice energy is significantly higher, indicating stronger intermolecular forces in this polymorph. Here I analyzed the pi-pi stacking interactions in pyrene. The lattice energy was calculated as minus 41.9 kilojoules per mole with pi-pi stacking contribution of about 50% of the total interaction. Comparing this with the hydrogen bonding, I found that hydrogen bonding in 5-fluorouracil accounts for about 60% of the interaction energies, showing its higher directional specificity. While hydrogen bonding stabilizes polar compounds, pi-pi stacking is crucial for the non-polar aromatic systems like pyrene, emphasizing their complementarity roles. To conclude, this study demonstrates the effectiveness of the computational tools in evaluating the molecular and crystalline properties. ORCA provided the optimized geometries, IR spectra, and electronic insights, while the CrystalExplorer enabled detailed lattice and interaction energy analysis. Overall, these results highlight the importance of DFT methods for understanding structural stability and molecular interactions, with potential application in material design and pharmaceuticals. That concludes my presentation. Thank you for your attention. I would be happy to take any questions.